So there are two ways to think about turbine efficiency. Now that we know the maximum power that a real turbine, an idealized turbine, could get out of a certain amount of wind, so we could establish what kind of efficiency that turbine would have, and then we can compare other turbines to it to see how they're doing relative to essentially an ideal, really, really great turbine. So in order to do that, the first thing we're going to do is actually figure out what would be the fantasy amount of energy that you could get out of the wind. So you have this wind coming in with some velocity, and if in your fantasy, you could think of taking all the energy out of that wind in order to get your, drive, in order to drive your power, your power needs. And if you did that, of course, you could do a first law analysis to figure out what that is. So that's what we're going to do right here. So from the first law of thermodynamics, we know that the amount of energy change in the fluid stream can be represented as the m dot times h, the enthalpy, v squared over 2, and gz at the inlet minus m dot h v squared over 2 minus plus gz at the outlet. So that you remember from thermo, and that's a first law analysis. So this is not whether this is possible or not. This is just how much energy is in the stream. If we could extract all of that energy, how great would that be? We're going to assume we're going to do that by changing velocities here. We're not going to be changing temperatures or anything like that. We know that for air, which is an ideal gas, that the change in enthalpy is equal to Cp dt. That is a change in temperature. And we're not going to have any of that. So we're going to assume that if the temperature changes 0, and also Zn equals Z out, so no surprise here, we're going to say, look, this energy that we're interested in, it's related to the velocity. We're going to try to get the wind velocity to give us the energy we're seeking, not trying to cool the gas down or whatever. So that's what we end up with just this, right? So we have, we have the inlet. The inlet is V1, the outlet is V2. So as we have V in equals V1, V out equals V2. And so we can write this amount of energy here. In the best possible case, we're going to say V2 is equal to 0. That is, we're going to take all the energy out with our turbine. So we would say the total available power from this stream, from this wind stream, is equal to m dot V1 squared over 2. We know that we can write that as m dot in terms of our velocities. So we're going to say that the total available power is equal to rho AT times V1 over 2. That's m dot over 2 times V1 squared. And so that gives us that the total available power is equal to 1/2 rho AT times V1 cubed. So this is very similar to what we were just looking at. Remember, we just figured out that we could get a certain amount of energy out that was related to V1 cubed, but the amount we could get was less than, was less than 1/2 of that. So we're going to go ahead and see, how well we really can do with a real turbine when the total available power in the flow stream is 1/2 rho ATV1 cubed. This is impossible. So this is like many first law analyses. This isn't possible to do. This is just the total energy that is available. So now we're going to define a power coefficient for this turbine. Power coefficient. There. And it's going to be called C sub P, and it's equal to the actual power generated divided by this theoretical impossible ideal. So 1/2 rho ATV1 cubed is what we know is available in the stream. We know it's certainly not possible to get all of it. But we do then know what the maximum power coefficient is for a turbine, because we know we just calculated P max, and we can compare that to rho ATV1 cubed, 1/2 rho ATV1 cubed, and see how we did. we found that P max was equal to 8 over 27. So P max of that same grouping was equal to 8 over 27 times rho, area swept by the turbine, V1 cubed, divided by 1/2 rho AT V1 cubed. And of course that comes out, these all just cancel, rho cancels rho AT, these are all identical except for the numbers in front. So 827 over 1/2 is the CP max. Obviously multiply up and down by 2, you get the maximum power coefficient for a turbine is 16 over 27, which is equal to 0.593. This has a name, it's called the BETZ number, B-E-T-Z number. And what that does is it allows you to calculate a power coefficient for a real turbine that you're working on or that you're dealing with, and you can see if its power coefficient is close to 0.593. This is the best any turbine could possibly do, is 0.593. So obviously this gives you a metric to decide, if one turbine's better than another, etc., based on how it's doing. If you've got a turbine that has a 0.59 power coefficient and someone tells you you need to make this better, you could tell them that you're wasting your time. This is as good as turbines can get. Is this power coefficient of 0.593. So anyway, we've got the ability to analyze wind turbines in an idealized model, and it gave us not only the way to calculate the power based on available data, it also allows us to assess whether any particular turbine is doing well compared to an idealized system. All right, that's it. Bye.